All right. Hello, class, and welcome back to Part B. This will be a brief part, I believe, I hope, where we're just going to review a little bit about coordinate systems, rotation matrices, and rotations in general. Now, I expect that most aerospace engineering students, assuming you're an aerospace engineering student, have seen rotation matrices, probably in the context of flight dynamics, where I have roll, pitch, and yaw, and so on and so forth. Our use here is a little bit different than that, in that we are rotating a fixed vector, right? A fixed vector through several different coordinate representations. So the vector does not change throughout this process. It's the coordinate system that we express it in which is going to change. So our use of the standard R1, 2, 3 rotation matrices is a little bit different. Right? That said, there are certain commonalities, right? In particular, of course, we're going to restrict ourselves. Of course, all our coordinate systems are going to be Cartesian coordinate systems. So in particular, they have 90-degree angles between the x, y, and z vectors, and they obey the right-hand rule. Basically, the right-hand rule is that your thumb, right, x vector, the index finger is the y, and the middle finger is the z. Of course, I'm using my left hand here. Sorry. The x vector is your thumb, the y vector is your index finger, and the z is your middle finger. So if your x and y point in these two directions, the sort of orientation of the z vector has to be sort of towards you. So it can't be pointing out towards the board because maybe you're like particularly disjointed or something, but most people's right hand only point one direction, hence it fixes the direction of that z vector. Or more importantly, in our case, if these are your x and z vectors, it fixes the orientation of the y direction. So that's the right-hand rule for coordinate systems. There's another right-hand rule for rotations. Basically, if this is a rotation, this is your axis, the rotation moves as your fingers curl about the thumb. Right? That's a positive rotation. But we'll come back to that in a second. Again, probably seen most of this stuff. What we're going to be using it for is, remember how many coordinate systems we introduced in Lecture 6. Particularly in this case, we're going to be focusing on the satellite normal, the perifocal, and the ECI coordinate systems. And at the end, of course, we're going to come back and talk about ECEF slightly. So really 3 or 4 coordinate systems. But there's actually two intermediate coordinate systems which don't get named, which we'll also talk about. Right. So what we're going to be talking about is rotation of the coordinate systems and not rotations of the vectors. Now, of course, they're very similar concepts, but they're a little bit different in how you use the rotation matrices. Okay. So specifically, the rotation. Well, we'll come back to the rotation matrices in a second. But that's the basics of the coordinate systems. These coordinate systems that we use, right, can be they might be inertial, they may be translating, and they may be rotating. In our case, they're not rotating, translating, or actually, the satellite normal is rotating, but most of them are not. So let's see. Right, rotation matrices, right, and rotating vectors. So this is actually the wrong illustration for this slide, because I couldn't find a better illustration, basically. So what we're looking at here is a rotation matrix, which allows us to take a vector and rotate it about an angle. In this particular case, we're rotating it about the y-axis, a positive rotation of that vector in the same coordinate system about the y-axis positively, obeying the right-hand rule. Okay. So these matrices allow us to take a vector and find the new vector which occurs once you've rotated that vector. So in particular, let's say we've got a vector here, right? V, and we want to rotate it. Let's make that. Let's see. That's X. That's Z. So actually, if we made the Z, Y would be into the board. So if we do it a positive rotation about that Y-axis would be actually that way. That would be a positive if that was a Y-axis. So let's of course, this is a rotation matrix about the Y-axis. So, but let's stretch our imaginations here a little bit. So say we've got a vector here. Here's the, let's see, where's the Z hat? X, Y, Z. So Z is pointing out of the board. So we have a vector here, V, and we want to rotate it about the Y-axis. Positive rotation. Make sure we're getting the right angle. Good. That's positive rotation. Positive rotation about the Y-axis to a new vector, V prime. Now this V doesn't have to lie in the XZ axis. That's the Z. It could be anything. It could be pointing up into our arbitrary space. But the rotation matrix allows us to compute that new vector, again, using the original coordinate system. Now, again, right, as I said, right, we have to pay attention to what the positive rotations are, right? So like in this particular case, right, I initially, let's say I made that the Z, then that was the Y vector, and a positive, that's Y hat, a positive rotation about that Y is actually going this way, right? Just using the right-hand rule, I align that Y vector, my thumb with the Y hat, and I get a positive rotation is going this way. So it's a little bit subtle, right? What are positive rotations and what are negative rotations? So again, right, we have a fixed or a sort of the classical 1-2-3 rotation matrices predefined for any rotation about an X, Y, or Z axis. So in particular, we call a rotation about the X-axis a R1 rotation, a rotation about the Y-axis a R2, and rotation about the Z-axis R3. And on the next slide, I'll give actually the formula for what those three matrices are. But again, I want to emphasize, right, that what we're doing here is rotating the vector V in the original coordinate system to a new vector in the same coordinate system. So these, in this case, the axes don't change, right? This is just a rotation of the vector. So this is important, right? Because generally there are arbitrary rotations, right? You can, this is what quaternions are actually all about. So take an arbitrary, in a given coordinate system, right? We can take an arbitrary axis, P, let's call it, and we can define a rotation matrix for rotation, again, positive rotation, got to check our angle, about that P axis, right? So that's a generalized rotation matrix, X, Y, Z. However, the rotation matrices that we are going to work with are rotation matrices which are predetermined, right? So this rotation matrix will depend very strongly on what the axis is. Here we're only using these three axes, rotations about these three axes, because the rotation matrices are very simple for those particular axes. But of course that is going to give us problems later on because we have to, we're going to be talking about the instantaneous rotation about a particular axis, and those axes are going to change. So we have to be careful. And that's, if you remember from part A, that's why I reversed the order of the orbital elements, which I just defined in lecture 6, to our new order, which we'll talk about shortly in part C. Right, so these are the three rotation matrices, right? They are very simple, given in closed form. Right? You can almost memorize them, right? There's a cosine, positive cosine on the diagonals. If you're rotating about the axis, right, nothing changes here. That's your zeros and ones. And then the only thing to remember is that the positions of the sines and cosines here. So hopefully I did these right. I guess y has an opposite sign to the R1s and R3s. Right. So you can write these down a priori and use them for reference, or just code them into MATLAB and as functions, and that's quite convenient. I've done it quite a few times. Now, in our case, what we're going to be doing is not rotating a vector. We're going to be rotating. We're going to be changing coordinate systems, which are defined by rotations about the x, y, and z axes. Now that makes our problem a little bit trickier, right? So let me go back to this slide, right? So if we take, if we're rotating a coordinate system, right? So say we have a fixed vector here. Let's say here's our fixed vector, v. And we have this v in the first frame. Let's say that's f1, and this is f2. And if we're rotating the frame and not the vector, then what we're trying to do is express this this vector in this new frame f2. So if we think about it, right, if we want the coordinates for this vector in f2, right, well, what have we done? In f1, right, the orientation of this vector is here, right, in f1. But in f2, it's below the x-axis. So if we were looking for this, if f1 made that f2, the vector would appear down here in the new f2 coordinates. So if you're rotating the frame at a positive angle, right, the expression of the vector in that new frame is actually a negative rotation of the vector. So actually, r in our vector in frame 2 is the let's see where we're rotating, z-axis, right, is a negative rotation of the vector, same vector as expressed in frame 1, right? So if we're rotating our coordinate system, the rotation matrix that we use is actually the negative of the rotation, the negative of the angle that we use to get from frame 1 to frame 2. Incidentally, by the way, rotation matrices have this very convenient quality that r of negative theta equals r transpose of theta. So you can also, this calculation, that it doesn't change much with the positive or negative angle, but you have to keep that in mind, right? It's r or r transpose. Yeah. So in this case, this problem is tricky. So what are we doing? We're taking this, so we're finding the position and velocity vectors in the perifocal, or actually satellite normal coordinate systems, right? So it's easy to find position and velocity in the perifocal coordinate systems, or the satellite normal slash PQW reference frame. So we're going to find r and v in that coordinate system, and then we're going to change the coordinate system, right, to ECI, right? So we want to find our vector in ECI given the vector in satellite normal. So in particular, what we're going to be looking for is our ECI defined by the rotation matrix from satellite normal to ECI, and where that's our position vector in satellite normal. So that's what we're going for. We're trying to get the rotation of, we're trying to reach ECI from satellite normal and then the vector, as expressed in satellite normal, will give, through this rotation matrix, the vector in ECI. Okay. That's even more complicated in our case because we actually, as we've defined these rotation angles, these orbital elements, actually we've been, in lecture 6, we went from ECI to satellite normal. So we had a sequence of rotations getting from the ECI to satellite normal. And so now we're going to have to reverse those rotations because what we're actually looking for is satellite normal to ECI. So we're going to express those position and velocity vectors in satellite normal and then convert to ECI. Again, it's a bit backwards, right, because that's not how we defined the rotations initially. And so when we defined our relative coordinate systems, we're going to be converting the ECI to satellite normal and not the other way around. Right? So you're not confused. You're doing well. In any case, so again, sequence of rotations. Rotation matrices can be used to calculate a sequence of rotations or a sequence of rotations of the coordinate system. Now, keep in mind that once you've rotated the coordinate system, the next rotation is a rotation of that new coordinate system. And then the next rotation is a rotation of that new coordinate system. So if we're going satellite normal to PQW to some intermediate coordinate system to ECI, right? Well, what does that look like? What order do we apply these rotations in? So for a vector, right, we may recall, right, if we're doing a roll, pitch, yaw rotation, for example, the order of the rotations is not the order of which the matrices appear. So if we're doing a roll, then a pitch, then a yaw, we first multiply the roll times the vector, then we multiply the pitch times that new vector, and then we multiply the yaw times that new vector, which is v prime prime. Right? And so the order at which these rotation matrices get multiplied is the reverse of the order in which the rotations occur. So the roll occurred first, then the pitch, then the yaw. So the order here is reversed. And it's the same thing for coordinate rotations. If we rotate the coordinates first about the x-axis, and then the y-axis, and then the z-axis, the rotations here are the same. Of course, we have our negative signs here in that case. So again, right, just to make this absolutely clear, or not, as the case may be, there's a difference between rotating a vector in a fixed coordinate system, right? So v naught, here, let's make it v naught, to v prime, it looks like it's called. So a given vector in a fixed coordinate system rotating about the, say, x hat vector, and then the z hat vector, right? That's rotation of the vector in that coordinate system, right? Conversely, right, if you're finding a fixed vector, and let's say it's v, and you want to rotate, we're not moving that vector, but we want to find its parameterization in our new coordinate system. Well, let's suppose we have two frames here, or three frames actually. Our initial frame, F1, we have first rotating about the x-axis. Well, sorry, the labels are wrong, but okay. Let's use our imagination, say that was our first frame, rotation about the x. And then rotation about the z. Now, again, right, this is our new, let's call it z prime axis. So that would correspond to a rotation about of the frame to frame 1, and then a rotation about of that new frame to a third frame, F3, let's call it. So we're rotating that, let's see, what are we rotating about the z actually? So first we rotate about x, and then we're rotating about z. So we're rotating about that that coordinate right there. So that the frame goes like that to our x prime prime, let's say, hat coordinate. So actually f1, f2, f3. So to do that, those coordinate rotations again, the angle is negative, right? So we're first applying, but the order is the same. We're first applying the negative rotation about the f1 coordinates, right, to get that same vector in the frame 2, or let's call it VF2. And then we do another rotation about a VF2 to get V as expressed in F3. Right. So this is why I'm not sure why this is. Oh yeah, okay, right. Yeah. So that's VF2 right there. So again, right, summarizing, if we obtain the principal axes of F2 by rotating the principal axes of F1 through a rotation matrix R, then if R is expressed in frame 1, we obtain R as expressed in frame 2 by using a negative rotation matrix, not the negative sign of the rotation, but a negative angle as applied to the position vector in F1. For example, which we'll come back to actually in part D of this lecture, for example, if you want to convert from ECI to ECEF, right? That's a rotation of your position vector in ECI about the rotation vector of the Earth, which is the z hat axis, so the Earth is rotating that way, by the local sidereal time, which we'll talk about later. But the axes from ECI to ECEF are defined by that rotation. If we want to find the vector in ECEF, which was really originally expressed in ECI, then it's a negative rotation of that negative theta LST. Well, again, we'll come back to that in part D of the lecture. Anyway, so that's wasn't meant to be too long. Hopefully I didn't extend it out too long. But now we'll come back and use that sort of background on rotation matrices to calculate our position and velocity vectors by rotating through the new orbital elements that we've obtained, right ascension of ascending node, inclination, and true anomaly, well actually technically true anomaly, and argument of periapse.